Section 4.5, Summary of Curve Sketching. Let's use the following guidelines to sketch some curves by hand. Domain, intercepts, symmetry, asymptotes, intervals of increase or decrease, local maximum and minimum values, and concavity and points of inflection. Let's first start by sketching the curve y equals 2x squared over x squared minus 1. So it looks like the first thing we should do is write out our domain. So this thing's undefined when x squared minus 1 equals 0, so it's going to be all of the points where that's not true. So the domain is equal to all of the x values such that x squared minus 1 is not equal to 0, which is the same thing as the x values such that x is not equal to plus or minus 1. For b, we need our intercepts. Notice that the x and y intercepts are both 0, because if you plug in 0 for x, you get 0 for y, and if you're looking for when y is 0, that's when x is 0. For c, we're looking for symmetry. If we plug in minus x for x, then we get minus squared, so it becomes the exact same thing as before. So it looks like this function is even, because f of minus x is equal to f of x. So that means it's symmetric around the y-axis, left-right symmetry. For d, we want to try to find some asymptotes. So we're going to look at some infinite limits to see if they equal a non-infinite number. And we're going to look at limits that equal infinity, or limits that don't exist in the form of infinity. So let's first look at our infinite limits. So our limits at infinity. So this is 2x squared over x squared minus 1. That means that if x gets super big, then this thing will probably end up just canceling a top and bottom and leaving us with 2. We can double check that by dividing the top and bottom by x squared. So 2x squared divided by x squared is 2. And then x squared divided by x squared is 1. And 1 divided by x squared is 1 divided by x squared. And then yes, as this thing moves to infinity, 1 over x squared gets really tiny. So this thing just equals 2. So that implies that y equals 2 is a horizontal asymptote. Notice I was able to plug in plus or minus infinity at the same time because our function is even. Now let's look for our infinite limits for vertical asymptotes. So I'm checking them at 1 because that's when my denominator is 0, so that's when my function will potentially blow up. So if I go towards 1 from the right, then the denominator gets super tiny. Dividing by a super tiny number is a super big number. So this thing goes and becomes infinity. And similarly, if I go in from the left, then the only difference is that it becomes negative in the denominator. So it becomes negative infinity. So I definitely have an asymptote at 1, but notice it doesn't matter if I plug in 1 or minus 1, because this function's even. So if I check for minus 1 from the right, I should still get infinity, or rather minus infinity. And if I check as x approaches minus 1 from the left, then I get infinity. Okay, so this thing has a horizontal asymptote at 2, and it has vertical asymptotes at 1 and minus 1. So x equals 1 and x equals minus 1 are vertical asymptotes. Let's look at our next check for curves, which is intervals of increase or decrease. So we have to check our derivative. By the quotient rule, that's x squared minus 1 times 4x minus 2x squared times 2x, all over the denominator squared. So that's x squared minus 1 squared. We simplify that, and we get negative 4x over x squared minus 1 squared. Because the x squared times 4x becomes 4x cubed over here, which cancels out with this 4x cubed. So now let's look at intervals of increase or decrease. So we'll look at the sine for f prime of x over an interval. So here's x, and it looks like our potentially bad numbers are 0 and plus or minus 1. Notice that plus or minus 1 are not critical numbers because they're not inside the domain of f. So we'll look at them anyway, but there's no way that they can be a maximum or minimum. So let's see, to the left of 0 it seems, because the bottom is always going to be not negative because we're squaring it. So if we ever have a negative number plugged in over here, it cancels with this negative and becomes positive. So that means all the way to the left of 0, these are positive. So it's increasing to the left of 0 whenever it's not equal to minus 1, obviously, because it's not defined there. Similarly, it's decreasing afterwards, because plugging in a positive multiplies by this negative and becomes negative. So it goes down after 0. Okay, it looks like it goes up and then down around 0. So by the first derivative test, if we want to find a maximum value, that's going to be at 0. And there are no minimum values. So f of 0 equals 0 is a local max by the first derivative test. Okay, the last thing is to check concavity and points of inflection. So we look for our second derivative. So that's x squared minus 1 squared times minus 4 plus 4x times 2 times x squared minus 1 times 2x, all over x squared minus 1 to the 4th. And we simplify that and get 12x squared plus 4 over x squared minus 1 to the 3rd. So let's look at where our second derivative changes sign. So potential numbers here are, again, plus or minus 1. So let's look at minus 1. Let's look at plus 1. Notice the numerator is never 0 because of that x squared, so there's no way to cancel out the positive 4. So if we are to the left of minus 1, then, well, it doesn't matter what happens in our numerator, it's always going to be greater than or equal to 0 because of the square. But our denominator to the left of the minus 1 becomes positive because minus 1 gets squared in the denominator over here, and then is bigger than that minus 1. So it's positive. Then if we go between minus 1 and 1, it's smaller, so the minus 1 dominates. So then it becomes negative, and then bigger is positive again. So it goes concave up, concave down, and then concave up. Notice there are no inflection points here, even though it looks like it's switching from concavity over here. Remember, minus 1 and 1 are not in our domain. So it does switch concavity, but it has no inflection points. Let's draw this now. Let's do our asymptotes first. We have one at 1. And one at minus 1. Let's put 0 over there. We also have a horizontal asymptote at y equals 2. It's concave up from minus infinity to minus 1, and it approaches those asymptotes, so it should look something like that. Then it goes concave down and has a local maximum at 0, so it should have this maximum and approach these asymptotes. And then it's symmetrical, so the exact same thing happens over here. Let's do another example and sketch the graph of f of x equals x squared over square root x plus 1. First, our domain. Well, our domain is whenever this thing is defined. So notice it's undefined when the denominator is 0 and when we take the square root of a negative number. So the domain is all of the x values such that x plus 1 is bigger than 0, not equal to 0. Okay, so that's the exact same thing as x values such that x is bigger than minus 1. And for b, we want to see our intercepts. Notice the x and y intercepts are both 0 again. Plugging in 0 for either one gives 0. And for c, if I plug in minus x, I do not get the value of f of x that I would get if I plugged in x. I don't even get minus. In fact, there's no symmetry here whatsoever. It's not even, not odd, not anything else useful in terms of symmetry. Let's look for some asymptotes. If I try looking at, let's say, x going to infinity, then I can try to see if I have a horizontal asymptote. So notice that if I take a look at this limit, the x squared on top completely dominates. This thing will end up going towards infinity. Because it does not equal a finite value, there is no horizontal asymptote. Let's see if there are any vertical asymptotes. That's when the denominator could potentially be 0. So let's try plugging in minus 1 and looking from the right. So that's equal to infinity again. But in this case, because we're looking at x approaching a finite value and we get a limit of infinity, that's a good thing if we want an asymptote, because this gives us a vertical asymptote. So now let's look for intervals of increase or decrease. We have to take our derivative. So that's square root of x plus 1 times 2x minus x squared times 1 over 2 rad x plus 1 all over x plus 1. A lot of quotient rule going on here. So this ends up becoming 3x squared plus 4x over 2 times x plus 1 to the 3 over 2, which is x times 3x plus 4 over 2 times x plus 1 to the 3 over 2. So if we do a number line, we can see when f prime changes sign. Potential numbers here, it seems, well, we have to start at minus 1, because below that's not in our domain. If we plug in 0, I think, is the only potential option here. Notice if we plug in minus 4/3, that could potentially be 0 too, but that's farther to the left of minus 1, so it's not in our domain. So the only values to really look at here are 0 and minus 1. So between 0 and minus 1, if we plug in, let's say, minus a half, then we end up with a positive here, and a negative here, so it's negative. And if we go above 0, let's say plug in 1, everything's positive, so looks like we're going down then, and then up. So we're decreasing, then increasing. So this tells us for f that f of 0 equals 0 is a local minimum. Because notice it just keeps going down until it hits 0. Okay, let's look at concavity now. So we'll do our second derivative. So that's another mess. 2 times x plus 1 to the 3 over 2 times 6x plus 4 minus 3x squared plus 4x times 3 times x plus 1 to the 1/2 all over 4 times x plus 1 cubed. Gotta love that quotient rule. So that simplifies to 3x squared plus 8x plus 8 over 4 times x plus 1 to the 5 over 2. And let's take a look at the signs. So for f double prime, again, we start at -1. But in this case, there are no other values that we could plug in here to make this thing equal to 0. Look at that thing on the top. If we were to try to do the quadratic formula, notice this thing kind of sits above over there somewhere. So it doesn't have real zeros. So this thing's always going to be positive if we plug in any value greater than -1. So our function is always concave up. So let's see if we can graph it now. We know we have an asymptote at x equals -1. And we know that our function is always concave up, and it has a minimum at 0. So it approaches the asymptote and hits a minimum at 0. It stays concave up all the way the rest. Okay, let's do it again for f of x equals x e to the x, our domain. Well, it looks like we could plug in any x value we want in this case. So our domain is R, or all real numbers. Our x and y intercepts, again, are 0. Plugging in x or y equals 0 gives us 0. It doesn't look like there's any symmetry here whatsoever. Plugging in minus for x doesn't give us minus f of x at all. So, or positive f of x, nothing. Let's look for asymptotes. So let's look for limits at infinity. Well, e to the x gets super big, x gets super big, product of two super big numbers is a super big number. So that goes to infinity. If you want, you can also see this for, how about minus infinity? But in that case, it's a little bit more tricky because e to the minus infinity is not a super large negative number. So as we look at minus infinity, we can rewrite this as x e to the minus x. And then now it's a super large negative number on top and bottom. So we can use L'Hopital's rule because this is indeterminate infinity over infinity. So taking the derivative, we get this is the limit of 1 over minus e to the minus x. Take derivative of the numerator and denominator separately using L'Hopital. And then we move e to the minus x back into the numerator So we get that this is the limit as x goes to minus infinity of minus e to the x. Well, as e goes to minus infinity, that just becomes super, super small, so this just becomes 0. Well, that's a finite number. This ended up becoming infinity, so we had no asymptote over there, but this is a nice finite number, so that means that y equals 0 is a horizontal asymptote. Because you can't just go and say something like, oh yeah, y equals infinity is a horizontal asymptote. Let's look for intervals of e increase or decrease. So our derivative by the product rule is x e to the x plus e to the x. And we can simplify that and get x plus 1 e to the x. So let's look now at a number line. Looks like our only potential problem here is at minus 1. That's where this thing would equal 0. So that's our critical number to look at. All right, to the left of minus 1, it seems like this thing will be negative. E to the x is always non-negative. And then to the right, it'll be positive. So it goes down, then up. It's decreasing, then increasing. Which leads us into our local minimum of minus 1. So f of minus 1 is minus e to the minus 1. 1 over e, or minus 1 over e, is about negative 0.37. So that'll tell us where to put our local minimum. Okay, last but not least, we want our intervals of concavity and our inflection points if we have any. So we take a derivative again. We get x plus 1 e to the x plus e to the x, which is the same thing as x plus 2 e to the x. So let's look at where our second derivative changes signs. Looks like we have potential issue at minus 2 this time. So it's negative before minus 2, positive afterwards, so that means that it's concave down and then concave up. So this implies that minus 2 e to the minus 2, which is about minus 2 minus 0.27, is an inflection point. So I think we can graph this now. We want to have a minimum at minus 0.37. So minus 1, so let's put minus 1 over here. Minus 0.37, that'll be our minimum. We have an inflection point nearby. Say over there, and we have y equals 0 is a horizontal asymptote as we approach minus infinity. So it should be concave up over here, approaching that asymptote. Then it goes and switches, and it's concave down, approaching that asymptote. Then it switches and becomes concave up. It hits that minimum value, and then it goes up. Yeah, so roughly something like that. Okay, let's sketch the graph of cosine over 2 plus sine x. Again, we can plug in anything, so our domain is all real numbers. Our intercepts, well, the y-intercept is when x is 0. So the y-intercept is f of 0, which is a half in this case. X-intercepts are when y is 0. So x-intercepts happen when x is equal to pi over 2 plus any integer multiple of pi. So plus n pi as long as n is an integer. So n is in the set of integers. So that's just when cosine, is 0. For symmetry, notice this thing's not even or odd. However, it does have, it looks like some sort of symmetry in terms of periodicity. Because if we plug in any x value plus 2 pi, that equals the same as if we just plugged in x. So that means that f is 2 pi periodic. So that'll help us, because now we only have to look at our graph from 0 to 2 pi, and then we can just fill in the entire rest of the graph by just extending it. Notice there are no asymptotes here. Sine, the smallest it can get is -1, so there's no way for the denominator to be 0 and blow up. And similarly, as we go towards infinity, we don't approach any specific number. Let's see intervals of increase or decrease. So let's look at our first derivative. By the quotient rule, we get 2 plus sine x times minus sine x minus cosine x times cosine x all over 2 plus sine x squared. So that equals minus 2 sine x plus 1 over 2 plus sine x squared. Let's see, where is this thing going to be 0? Well, that's when 2 sine x plus 1 is equal to 0. So that's when sine of x equals minus a half. If we draw a unit circle really quick, we can see that from 0 to 2 pi, that happens at this 36 to 90 triangle over there. That's when sine is closer to the y value is closer to the x-axis for that 36 to 90 one. And then it happens again over there. The y value has to be negative because we're looking for minus a half. So that's at x equals 7 pi over 6. And x equals 11 pi over 6. So now that we have our potential critical numbers, let's take a look at what this thing, the sign of the derivative. Okay, so let's put 7 pi over 6 somewhere over there. We'll put 11 pi over 6 over here. We only have to look from 0 to 2 pi because of the periodicity. So from 0 to 7 pi over 6. So we move along over here. Well, in that case, this thing is going to be bigger than minus a half. So this thing will end up positive over there. The denominator is always positive, so it'll be negative because of the negative out in front. Then from 7 pi over 6 to 11 pi over 6. So over here, the exact opposite will be true. This thing will be negative. So the negative times the negative will be positive. And then from 11 pi over 6 to 2 pi, we have that issue again, where this thing becomes positive, so the entire thing is negative. So it goes decreasing, then increasing, and then decreasing. So that leads us into f of 7 pi over 6, which is minus 1 over rad 3, if you plug it in, as a local minimum. because it just goes down like that. And similarly, 11 pi over 6, we can see that it's going to be a local maximum. So that's positive 1 over rad 3. Last but not least, we have to check for concavity. So we'll use our first derivative. We'll take the quotient rule again, and we get that f double prime is equal to minus 2 cosine x times 1 minus sine x all over 2 plus sine x cubed. So we'll look for where this thing changes sign. Oops. And it seems like, well, again, we'll go over 0 to 2 pi. It seems like we have issues when this thing is going to be 1, because from 0 to 2 pi, then when sine is 1, when cosine is 0. So I think that's going to happen at pi over 2. Yeah, 1 minus sine of pi over 2 will definitely make this thing 0. And again at 3 pi over 2. That'll make cosine 0. Okay, so from 0 to pi over 2, it seems like we have sine from 0 to pi over 2 be nice and positive, going up until we get to 1. So we have everything positive, it seems, up until pi over 2, but then the negative out in front makes it negative. So then from pi over 2 to 3 pi over 2, we end up with most of our stuff staying positive. 1 minus sine, there's no way that could be negative. However, cosine in that case is negative from pi over 2 to 3 pi over 2, because it's the x value. So the two negatives cancel, become positive, and then it becomes negative again thereafter. So we're concave down, concave up, and then concave down. So I think that gives us inflection points. So we have inflection points at pi over 2, 0, and 3 pi over 2, 0. Let's try graphing this now. Okay, this thing is y-intercept of a half, and it has, well, let's put pi over here, it has an inflection point over here, and then it has another inflection point over here, and a minimum at 7 pi over 6, so roughly over there, and a maximum right before we get to 2 pi at 11 pi over 6, so somewhere over there. So let's see if I can do this. We want to go over here, change concavity, and then bounce back up, change concavity again. So it should look something like this, and then it repeats, because now we can extend it past our value 2 pi by utilizing the periodicity. So Go down, and there we go. And that's at minus pi. All right, decent rough sketch. Okay, how about y equals ln of 4 minus x squared? Well, first our domain. So that's going to be all of our x values such that 4 minus x squared is positive, which is the same as x values such that x squared is less than 4. Well, we can keep going. Solve for x, we get this our x value such that absolute value of x is less than 2. Well, absolute value of x being less than 2 is just the interval from minus 2 to 2. So it's not defined outside of that interval. Let's look at our y-intercept. So that's f of 0, which is equal to natural log of 4. Let's look for where y is 0 to find the x-intercept. So y equals ln of 4 minus x squared is equal to 0 when 4 minus x squared is equal to 1. Natural log of 1 is 0. So that's when x squared is equal to 3. So our x-intercepts are at plus or minus root 3. Okay, let's look at symmetry. If I plug in minus x, then it gets squared. So this function is even, because the minus will cancel. Let's look for asymptotes. It looks like if we look at limits at infinity, they're not going to be any real limits. So let's just look for where this thing potentially blows up. We'll look for vertical asymptotes. So that's at 2, because that's when natural log is 0. So as we approach 2 from the left, this becomes the natural log. We'll look at the natural log of 4 minus x squared. We can see that this thing goes to minus infinity. As we approach 2 from the right, it's the exact same thing. Again, it gets squared. So it doesn't really matter. So, sorry, minus 2. Because when you square it doesn't matter. So minus 2. Notice that we had to approach 2 from the left because 2 from the right is outside our domain. And similarly, minus 2 from the left is outside of our domain. So these were the only values that we could approach. Okay, so that means we have some vertical asymptotes at x equals 2 and at x equals minus 2. Okay, intervals of increase or decrease. So our derivative now is minus 2x over 4 minus x squared, just by the chain rule. 1 over 4 minus x squared times derivative. So that's actually not too bad, at least compared to the other ones we've been doing. And this thing, well, we're going from minus 2 to 2 for x. We have potential problem at 0 for our numerator. So that's our critical number. If I look to the left, it looks like it's going to be positive because the negatives will cancel in the numerator. And if I look to the right, it should be negative. So that means it's going up and down. It's increasing, then decreasing, which means that by the first derivative test, f of 0, which is equal to ln 4, is the local maximum. And lastly, let's look for concavity. So our second derivative, which is 4 minus x squared times minus 2 plus 2x times minus 2x. So unfortunately quotient rule again, but not as bad. You get 4 minus x squared squared in our denominator. That simplifies out to minus 8 minus 2x squared all over 4 minus x squared squared. So let's look at our second derivative. From minus 2 to 2. Notice this thing from minus 2 to 2 will never eclipse the minus 8. So there are no numbers here for this thing to be 0. Same thing for our denominator. There's no way for this thing to be undefined. So this thing has the same sign throughout. So if we look from minus 2 to 2, I could just plug in 0 for x, and you can see that this thing's going to be negative everywhere. So this thing is always concave down. Let's try graphing it now. Alright, we got a maximum at 0, L, and 4. Let's pretend it's over there. So that's 0, L, and 4. And we have intercepts at plus or minus rad 3 for x, so let's put those over here. So that's rad 3, 0, and that's minus rad 3, 0. I almost forgot, we've got asymptotes too. So let's put those in. So this is x equals minus 2, and x equals 2. And it's concave down the entire time. So it goes concave down approaching this, hits our maximum, and still concave down. Alright, not too bad. Let's talk about slant asymptotes now. If the limit of the difference between f and the line mx plus b is equal to 0, then the line y equals mx plus b is called a slant asymptote, because the vertical distance gets, arbitrarily small, so our function gets closer and closer to this line y equals mx plus b. Let's do an example by sketching the graph of x cubed over x squared plus 1. Again, we look at our domain and see that it's all real numbers. You can plug in anything you want. There's no way for our denominator to be 0. So x and y intercepts are both 0. Notice if you plug in a negative, it doesn't change the bottom, but it makes the top negative. So that means that our function is actually odd, because f of minus x is equal to minus f of x. Let's now look for asymptotes. Okay, so notice as we go towards infinity, this thing goes towards infinity. So there's definitely no horizontal asymptote. As far as vertical asymptotes, again, our domain is all real numbers. There's nowhere for this thing to be undefined, so we're not going to have any vertical asymptotes. However, remember, we have slant asymptotes if the distance between this and some linear function goes to 0. So let's see if we can try to pull out a linear function. We can do this using long division. So let's do x cubed divided by x squared plus 1. So we try putting x squared plus 1 into x cubed. We put some placeholders in. So 0x squared plus 0x. Notice that x squared fits into x cubed x times. So then we multiply x squared plus 1 times x. We get x cubed plus x. We subtract, and we get minus x. So that means that x cubed over x squared plus 1 is the same thing as x plus minus x over x squared plus 1. So f of x equals x cubed over x squared plus 1 is equal to x, instead of plus minus, I'll just do minus x over x squared plus 1. Because this was our remainder, that x, that's what goes over there, that minus x. Okay, notice in general, you have the possibility of a slant asymptote whenever you have a rational function and the degree of the numerator exceeds the degree of the denominator. Because then it goes towards infinity, but there still could be a slant asymptote. This suggests that we should choose x to be our linear function that we get close to. Let's test that. If I do f of x minus x, well, that's the same thing now. We see that as minus x over x squared plus 1 by just subtracting x from both sides. Well, we can divide the top and bottom by x. This is always how we take a limit as we go towards infinity. Sorry, divide top and bottom by x squared. Okay, make this go towards infinity. This goes to 0, this goes to 0, so we end up going to 0. So this goes to 0 as x goes to plus or minus infinity. So that's another way of saying that the limit of this thing over here is 0 as we go towards plus or minus infinity. So that's the exact definition of a slant asymptote. So that implies that y equals x is a slant asymptote. Okay, let's look for intervals of increase or decrease. So we take our derivative, and unfortunately another quotient rule. Unless you like the quotient rule, in which case this is very fortunate for you. We simplify it and we get x squared times x squared plus 3 all over x squared plus 1 squared. So we look for where the derivative changes signs so that we can use our test for increasing and decreasing. Looks like the denominator is fine. Numerator over here is also going to be fine. So the only issue over there is that part of the numerator at 0. So it seems like, well, if I go to the left of 0, any number I plug in is going to be squared, it's going to be positive. And similarly, any positive number is going to stay positive. So this thing's always increasing except at 0. Alright, if I look at f, well, if it's always increasing, there's no local max or min. Let's look for concavity. We take our second derivative, and we get a nice unholy mess, x squared plus 1 squared times 4x cubed plus 6x minus x to the 4th plus 3x squared times 2 times x squared plus 1 times 2x all over x squared plus 1 to the 4th. So that ends up becoming 2x times 3 minus x squared over x squared plus 1 to the 3rd. Let's look for where this thing changes signs. Looks like we have potential numbers at minus rad 3, 0, and rad 3, because those are numbers you plug in over here to get 0, over here to get 0, and notice the denominator will never be 0. So if I go to the left of minus rad 3, then it gets squared all over here, so I don't have to worry about it. And to the left, oh, well, then this thing's actually bigger, so that this thing's negative, so it becomes positive. From minus rad 3 to 0, that's when it'll be negative, because it's a negative number, and then this thing's negative, but this thing's positive then. From 0 to rad 3, it'll be positive, because now we're looking at a positive number, and plugging it in, and it's still smaller than 3 when you square it. But then past rad 3, it becomes bigger, so then this thing becomes negative, and everything else is positive. So it looks like we're concave up, then concave down, then concave up, and then concave down. So we end up with 3 inflection points. So we have inflection at minus rad 3, minus 3/4 rad 3, at 0, 0, and at rad 3, which we plug in to get 3/4 rad 3. Remember to always plug back into your original function. So all of these are inflection points. To graph this thing, let's start with our slant asymptote, because that was the most exciting thing. So let's do a nice slant y equals x. And then we have inflection points over here. And let's say over here, let's call this rad 3, 3 rad 3 over 4. And over here, this can be minus rad 3. Minus 3 rad 3 over 4. So it goes concave up until it hits the inflection point, and then it switches and becomes concave down, and then switches and becomes concave up again, and approaches our asymptote. Oops. And approaches our asymptote. I'm not 100% happy with this guy because it should be approaching the asymptote. Okay. There you go, that's a pretty good graph.